Hey class, I wanted to record a video for our integrated assessment. And by the way, I'm going to push back this integrated assessment until Friday. So Wednesday, tomorrow, we'll just do the two force assessments. Because I haven't had a chance to explain the integrated assessment and what that is. So the integrated assessment, there are 3 of them throughout the semester. And they're just like regular assessments. You get 3 tries on each, except that they're integrated, meaning they combine more than one concept. So the first integrated objective is, can you combine forces and motion? In other words, if you know the forces acting on the object, can you find the acceleration and then use the acceleration to understand the motion? Or maybe you can do it conversely. If they give you information about the motion, can you find the acceleration and thereby understand the forces acting on it? Because we know that, the net force on an object is related to its mass times acceleration. All right, so here's an example of what I mean. So we have this person who is pushing a very heavy block up a hill that is sloped 12 degrees. And he's pushing the block with 505 newtons directly up the hill. And the block has a coefficient of friction on the ground of 0.1. So low coefficient of friction. So that's good. So the question asked, how fast will the block be moving after it's been pushed 14 meters? So you can see it's indicated here that the initial velocity of the block is 0. Okay, so what's the game plan here? How are we supposed to know how fast it's moving? Well, you might think, hey, if I know the acceleration, I might be able to understand how fast it's moving. But how can I get the acceleration? Oh, I have to use the forces to solve for the acceleration. Here's our integrated part. All right, so we start off with just a force problem. And one of the first things we do, obviously, with a force problem is we draw a free body diagram, which I've done so here, right? And we have our x-axis, positive x-axis over here, positive y-axis going up. X-axis is parallel to the slope, and y-axis is perpendicular to that. So obviously, I mentioned he's pushing directly up slope, so the push force is going directly in the positive x direction. And there's friction, which acts in the opposite direction of motion. So friction will be going in the negative x direction. And then the normal force, remember, isn't always directly up, but it's always perpendicular out of the surface. So we drew our y-axis perpendicular to the surface, so the normal force is going along the y-axis. And then gravity is going straight down. And remember, gravity is off axis here. So whenever you draw a free body diagram and you have one force that is off axis, you need to break it up into its components. So remember, it's just a right triangle. All vectors are just right triangles. Yeah, the x, the y component and the x components are the sides of the triangle, and the magnitude is the hypotenuse. All right, and this angle is 12 degrees here, so that's the x component, and that's the y component. And you can see that the x component of gravity is pushing the block downhill, so it'll be negative. Well, what do we want to do? We want to find the net force in each direction, and because we know that the net force is equal to the mass times the acceleration in that direction. So we'll start with adding up all the forces in the y direction. So we just consult our free body diagram, which we just drew. So we have the y component of gravity going in the negative y direction. So that's why it's negative there. And then we add the normal force to that, which is in the positive y direction. So we add up those forces. That's our net force in the y direction, which is equal to the mass times the acceleration in the y direction. And in this problem, the block is staying on the surface, it's not going under the surface, or it's not being pulled off the surface. So you can infer that the acceleration in the y direction is 0. So the net force in the y direction must be 0, and therefore the normal force is just going to be equal to the y component of gravity here. And note that the normal force isn't always this. You have to go through the force balance in order to be sure. Okay, so the normal force is going to be equal to the mass times gravity times cosine of 12 degrees. So as you can see, consult your triangle. The y component of gravity here is touching this 12 degrees, so it's adjacent to it, so we want to use cosine. All right, so we solve for the normal force. Now we want to do the same kind of thing and add up the forces that are in the x direction. So we have F push in the positive x direction. We have the friction force going in the negative x direction. And we have the x component of gravity as well. Don't forget that. This guy down here, gravity is pushing you downhill a little bit. So when you add up all those together, that gives you the net force in the x direction, which is equal to the mass times acceleration in the x direction. All right, and then we can just plug in our numbers. Our push force is 505 newtons. The friction force is the normal force times the coefficient of friction. And we solve for the normal force up there. And then we have our x component of gravity. And our x component of gravity is opposite that 12 degrees, so it'll be sine of 12 degrees times the magnitude of the gravitational force, which is just mg. So all of those together is going to equal mass times acceleration in the x direction. So I'm just going to divide through by mass, so mass is going to cancel in these terms and divide by that term. We have 505 newtons divided by 120 kilograms. Both of those are times by gravity, so I have 9.8 there. Cosine 12, and our coefficient of friction is 0.1. And then that's our x component of gravity. And we just plug in those numbers, and we find that the acceleration in the x direction is 1.21 meters per second squared. Lovely. We're done, right? Oh, no, wait, there's just a little extra part here, because what the question asks is how fast is the block moving after being pushed 14 meters? Well, now that we know the acceleration, that's going to be easy. So we want to use the kinematic equation that shows how we want to use the kinematic equation that shows how velocity evolves with distance. So we're going to use this equation, v squared equals v naught squared plus 2 times displacement times acceleration. And now we know everything in this equation. The initial velocity is 0. The displacement is 14 meters. It moves 14 meters uphill. And we've solved for the acceleration now. So we can just plug those into our calculator. And we get that the final velocity of the block after it's been pushed 14 meters is 5.82 meters per second. Huzzah! All right, so that's an example of one of the integrated problems that you'll be tested on Friday. And there's a lot of problems on the homework, actually, that are integrated as well. And so hopefully you've been looking at those and using similar strategies to understand those. All right. Cheers. See you tomorrow.